Hello everyone. On behalf of all co-authors, allow me to extend a warm welcome to you. Let me briefly introduce myself. My name is Manije Hassan Abadi, and I am delighted to be here today to talk to you about our research. I'll gladly answer any of your questions at the end. What I'm going to talk about today is new trends toward the application of fractional calculus in the mathematical modeling of biological systems. Let me start my presentation with a summary of significant points in our work. A generalized version of fractional models is introduced for the COVID-19 pandemic, including the effects of isolation and quarantine. First, the general structure of fractional derivatives and integrals is discussed. Then, the generalized fractional model is defined from which the stability results are derived. Meanwhile, a set of real clinical observations from China is considered to determine the parameters and compute the basic reproduction number, i.e., R naught is approximately equal to 6.6361. Additionally, an efficient numerical technique is applied to simulate the new model and provide associated numerical results. Based on these simulations, some figures and tables are presented, and the data of reported cases from China are compared with the numerical findings in both classical and fractional frameworks. Our comparative study indicates that a particular case of general fractional formula provides a better fit to the real data compared to the other classical and fractional models. There are also some other key parameters to be examined that show the health of society when they come to eliminate the disease. My talk is divided into 5 parts. First, I'll start with preliminary notes. Second, I will talk about a general fractional COVID-19 model with isolation and quarantine effects. Then, I will look at a new numerical technique to simulate the model. Next, the results and discussion are followed. And finally, some concluding remarks close the presentation. In this part, some preliminaries are presented about the recently introduced general fractional derivatives and integrals, the general form of left Caputo and Riemann-Liouville fractional derivative would respectively be written by equation 1 and 2, in which alpha is the order of fractional derivative. Also, under some conditions of the kernel function KL of t and entirely monotone function ML of t exists for all t greater than 0 such that the convolution of kernel and monotone functions are defined by equation 3. Moreover, the relationship between the alpha derivative and negative alpha derivative of function ft is defined by equation 4, where negative alpha derivative represent the general form of Riemann-Liouville fractional integral defined by equation 5. Following the same concept as above, the right Caputo and Riemann-Liouville fractional derivatives could be respectively stated by equation 6 and 7, and the right-sided Riemann-Liouville fractional integral would be described as equation 8. Now, 3 particular cases are introduced here according to the recent definitions. First, the general kernel and the power function constitutes the associated kernel for the integral operator 5. Second, the kernels and Mittag-Leffler functions would be considered in equation 10. Finally, the Caputo-Fabrizio derivative is formulated by equation 11, in which the kernel is the exponential function. Furthermore, capital M of alpha would be the normalization function such that M of 0 equal M of 1 equal 1. In this section, the new model of COVID-19 with isolation and quarantine effects is analyzed in both integer and fractional order frameworks. As a part of this section, the non-negativity of the solution is investigated. Then the feasible region is presented, which is shown to be positively invariant. Finally, by introducing the basic reproduction number, the equilibrium points and their stability are explored. The threat posed by COVID 19 to millions of people worldwide is becoming a real threat and a severe health risk. Isolation and quarantine could be introduced as effective and practical solutions to decline and eradicate the disease transmission rate. Coronavirus can spread through people who have clinical symptoms and are vulnerable to infection. As a result, an ordinary differential equation system which describes the disease could be derived as below. And this slide we introduce the other parameters. Next, we describe lemma 1 and its proof and shown the above model has a non-negative solution for any time greater than 0. Moreover, the limit of capital P of t when t tends to infinity is less than or equal to beta over psi. In the next lemma, by considering the non-negative initial conditions for the system 12, the feasible area Z be specified by equation 14 is positively invariant. In this section, a general fractional derivative which is presented in previous section would be applied to modify the COVID-19 model dynamics 12. Thus, the following new and general fractional model is available here, together with non-negative initial conditions. Let P0 denote the disease-free equilibrium point by means of the model 15. The basic reproduction number of the model 15 could be obtained by means of a next-generation matrix that can be obtained from a spectral radius of the multiplication of two matrices capital F and inverse of capital V in the disease-free equilibrium point. Okay, in the next step, we've shown that the model 15 is stable locally. If R0 is less than 1 at the equilibrium point P0, then the system 15 would be locally asymptotically stable. At the endemic point, the equilibrium is then obtained by equation 17. The above result can be inserted into epsilon of t, then the capital F of lambda star is obtained, in which B0, B1, B2 are described as below. In this case, B2 is greater than 0. B0 is negative if R0 is greater than 1, and it is positive when R0 is less than 1. Therefore, the sign of B0 depends on the value of R0. The above discussion is summarized in the next theorem. Turning our attention now to the next section. This section proposes an efficient method for solving the system of general fractional equations 15 numerically. Let me elaborate further about a predictor-corrector method by considering these notations. In the following, a Volterra integral equation is expressed by applying the general fractional integral 5 to each side of the first equation in 15. And in the next equation, by replacing t by t plus 1, in the previous equation we obtained the equation 19. Then the trapezoidal quadrature formula can be used to approximate the integration part in 19. After calculating interpolation polynomial and applying the equation 21 in 20, finally we obtain the corrector formula for the first equation of 15 as follows. For this purpose, instead of equation 21, the approximation f hat k plus 1 is employed for the integration parts in 19 and 20. Thus, instead of equation 2020, the following result is obtained. The predictor formula is then derived as the following equation. And then we can repeat this method for the remaining equations in 15. I'd now like to move on to the results and discussions. According to the COVID-19 real data from Wuhan, China, the values of parameters were extracted from reference 2. Table 1 shows the results that were determined realistically. The system 15 was simulated by applying the power law, Mittag-Leffler, and exponential kernels in figures 1 to 8. And for different values of fractional orders, also the time was measured in the units of days. Figure 1 related to susceptible people. Figure 2 vulnerable individuals. Figure 3 clinically symptomatic infected people. Figure 4 asymptomatic infected persons with hardly any clinical signs. Figure 5 quarantined people. Figure 6 under treatment individuals. Figure 7 people who are recuperated. And finally, figure 8 related to seafood market people who visit the markets and purchase the food, get infected and spread it throughout the environment. Table 2 shows the absolute and relative errors via using the power law kernels for different fractional orders. The best fractional order is 0.99. Table 3 shows the absolute and relative errors via using Mittag-Leffler kernels for different fractional orders. The best fractional order is 0.99. Table 4 shows the absolute and relative errors via using the exponential kernel for different fractional orders. Also, you can see the best fractional order is 0.99. Table 5 compares the absolute and relative errors for the integer order model 12 and the three particular cases of fractional formula 15. This table indicates that the best solution is associated with power law kernel. Also, you can see the fractional results in all cases is better than the integer order counterpart. Figure 9 displays the fractional simulation by considering the power law, Mittag-Leffler, and exponential kernels versus the real reported cases of COVID-19 in China. We will examine the effect of some parameters on the system dynamics hereinafter. The amount of infected people for certain values is illustrated by theta 2. This amount declines very quickly when the infection rate in the seafood market decreases, as illustrated in figure 10a. Consequently, closing the seafood market could be a vital act by the Chinese government in order to prevent the infection from spreading further. Figure 10b shows proportion of the asymptomatic infection parameter omega graphically. The number of infected individuals decreased by a reduction in the value of omega. Thus, the asymptomatic infection plays a vital role in the infection development, so it is necessary to educate people about how to avoid contact with such individuals. Figures C, D, E depict the effect of parameters sigma 2, kappa V, and tau m, respectively. It could be obvious that the number of infected people decreased by the reduction of these parameters. Consequently, the quarantine class would be extremely crucial for the COVID-19 modeling. Now, I'd like to recap the main points of our presentation. This research investigated a new fractional model of COVID-19 by considering the effects of isolation and quarantine. The model was first developed through ordinary time derivatives and then modified by applying the general structure of fractional operators. The model stability was discussed, and the parameters were estimated based on a realistic situation in China. So the basic reproduction number was calculated. Simulation results were obtained through an efficient numerical method used to solve the associated general fractional differential equations. As a result, some graphs and tables were provided for various fractional orders and different kernel functions. It was shown that a particular case of fractional model fits the reality more accurately than the other classical and fractional cases. Graphically, some other parameters with their effects on the model behavior were examined. which could act as a control for the disease eradication. Thank you for your attention.